The lights in your house just flickered. 1 second. Maybe 2. You didn't think about it. But somewhere in America, a room full of engineers just stopped breathing. Because that flicker, that tiny interruption, it means something slipped, something massive, something that wasn't supposed to move.
I'm standing in a control center right now. 12 screens, 40 operators, and every single one of them just looked up at the same wall display.
The number they're watching?
60.00. That's the heartbeat, the rhythm of the entire American grid.
60 hertz, 60 cycles per second. That's the frequency that keeps 330 million people alive. When that number drops, even by a fraction, power plants start tripping offline. Factories shut down. Hospitals switch to backup. And if it falls far enough, cascading blackout, city by city, state by state. But here's the thing, that almost never happens. Why?
Because behind every socket in America, there's a hidden system, a machine built to prevent collapse. We call it the Blackout Factory.
It's not one building. It's a 3-layer fortress. The brain, the muscles, the insurance. And today, we're going inside all 3. Chapter 1. The brain. Inside, the control room. The first layer is invisible to almost everyone. Tucked behind unmarked doors, hidden in suburban office parks, protected by fences you drive past without noticing. These are the ISO and RTO control centers, the regional command rooms that balance supply and demand across entire portions of the country. There are 7 major ones. Together, they oversee about 2/3 of American electricity. And inside each one?
I'm walking through security now. Badge check, man trap door, another badge check.
No phones allowed past this point. The hallway is quiet, almost too quiet. Then I step through the final door, and the scale hits me. A curved wall of monitors, 50 feet wide, maybe more. Each screen showing a different slice of the grid, power flows, voltage levels, generator outputs, transmission lines glowing green, yellow, red.
It looks like mission control for a space launch. Except this launch never ends.
These operators work in shifts, around the clock, watching the grid breathe. They're not just monitoring, they're predicting. Every 5 minutes, sophisticated software recalculates the entire system. It asks one question over and over. What happens if something breaks right now?
That's the N1 rule. The grid must survive the loss of any single major component.
Any generator, any transmission line, any transformer. If the answer is, we'd be fine, the system holds steady. If the answer is, we'd be in trouble, operators start moving power.
Rerouting flows, calling generators online, all before anything actually fails.
Think about that. The grid is constantly preparing for disasters that haven't happened yet, and it's doing it in near real time, using thousands of high-speed sensors called phaser measurement units, PMUs. They sample the grid 30 times per second, feeding data back to these control rooms faster than you can blink.
Yeah, look at this.
One operator shows me his screen.
He points to a line in Texas. It's running hot. 92% capacity. He's already watching the weather forecast for that corridor. Patterns. Temperature. Humidity.
This is the brain of the Blackout Factory. Not a supercomputer. A room full of humans, making thousands of small decisions every single day. And if they do their job perfectly, you never even know they exist. Chapter 2. The muscles. The substation that can't fail. But brains need muscles. And the muscles of the grid? They're made of steel, copper, and oil. Lots of oil. Substations, switchyards, transformer banks. The physical hardware that actually moves electricity from power plants to your home. There are over 55,000 substations in America. Most are small, neighborhood scale. But some are massive, critical, the kind of facility where a single failure could black out a major city.
I'm at one now, so no to new.
I can't say exactly where, but I can tell you what I'm seeing. A fenced compound the size of 4 football fields. Towers of steel. Ceramic insulators as tall as a person. And transformers create, huge gray boxes create, humming with raw power. The sound is constant, a low, deep vibration you feel in your chest.
This is where high voltage transmission meets the distribution network. Power comes in at hundreds of thousands of volts. It leaves at levels your house can actually use. And the equipment handling that conversion, it cannot fail.
The transformer I'm standing next to weighs over 400 tons.
Inside, there's a core of specialized steel wrapped in copper windings. The whole thing is submerged in mineral oil for some thousands of gallons, tasked to keep it cool. Touch the casing. It's warm, even on a cold day, because right now, this single machine is handling enough electricity to power a small city.
Substations like this are protected by layers of redundancy. Multiple transformers, multiple feeders, circuit breakers that can isolate a fault in milliseconds. And protection relays specialize computers watching every parameter: voltage, current, temperature, phase angle. If something goes wrong, the relay acts before a human could even react, isolating the problem, protecting the rest of the grid.
A technician walks me through the breaker yard.
These aren't light switches. They're machines filled with insulating gas, designed to interrupt currents of 50,000 amps or more. When they trip, the energy released is like a small explosion. Contained, controlled, but violent. He tells me they test these regularly. Because when you need them, there's no second chance.
This is the muscle of the Blackout factory. Thousands of substations, working in concert, day and night. But there's a catch. Comment your guess. What's the one piece of equipment here that takes the longest to replace if it fails? Chapter 3. The bottleneck. The transformer factory. Why? 18 months. It's the transformer. That 400-ton machine we just saw? If it fails catastrophically, you can't just order a new one. Average lead time for a large power transformer: 18 months. Sometimes longer, sometimes much longer.
I visited a transformer manufacturing plant. Not many left in America. Maybe a handful that can build the biggest units.
The factory floor is enormous.
Cranes overhead.
Move it over.
Move it over. Watch the load. Specialized winding machines. Vacuum chambers for drying insulation. And the smell of oil. Everywhere.
Here's why these machines take so long. Every large transformer is custom built, designed for a specific substation, a specific voltage, a specific climate. The steel core is assembled from thousands of thin laminations, each one cut precisely, stacked by hand in many cases. The copper windings are wrapped with exact tension, insulated with special paper. Then the whole assembly is dried in a vacuum oven for days.
One engineer told me they measure moisture content in parts per million. If the insulation is even slightly damp, the transformer will fail early. So they bake it.
Tested.
Insulation test running. Bake it again. There's no shortcut.
And then there's the problem of moving it. A finished transformer might weigh 800,000 pounds, too heavy for most bridges, too wide for most roads. Special rail cars, specialized trucks, route surveys that take months. One utility told me they started planning the delivery route before the transformer was even built.
At the loading dock, I watched a transformer get lifted onto a custom trailer. Axles. Hydraulic leveling systems. A chase vehicle driving ahead to check every overpass. The journey to the substation, 15 miles per hour. Maximum.
This is the bottleneck of the Blackout factory. Everything else can be repaired in days, weeks at most. But a large power transformer? Lose one at the wrong time, in the wrong place, and you've got a problem that lasts a year, which is why the grid has insurance. Chapter 4, the insurance. Black Start plus mobile substations. Insurance Layer 1. Spare transformers. Utilities across America share a fleet of emergency transformers, stored strategically, ready to deploy. It's called the Spare Transformer Equipment Program, STEP, coordinated across the industry. The idea is simple. If a critical transformer fails, you don't wait 18 months. You pull from the reserve.
I saw one of these spares. Sitting on a concrete pad in a fenced lot. Covered in weather protection. Connected to nothing. Just waiting. It's been there for years, never used, and that's exactly the point.
Insurance Layer 2, mobile substations. These are trailer-mounted transformer units, smaller than the permanent installations, but designed to roll in fast. After a hurricane, after a wildfire, after any disaster that takes out grid infrastructure, they can restore power to critical facilities within hours.
The mobile unit I inspected was the size of a semi-truck. Cables coiled on racks. Switchgear built into the frame. The operator told me he's driven this thing across 3 states in a week during storm season. Where it's needed, it goes.
Here's what I want you to remember. Every second, across America, electricity flows, silently, invisibly, powering everything you depend on. The lights in your home, the servers holding your data, the machines in hospitals keeping people alive. It all rests on this hidden system. This interlocking network of control rooms and substations and transformers and people. The Blackout factory. And the result? 60 hertz. Stable, steady, reliable. The heartbeat of a civilization. You didn't notice it today. You weren't supposed to. That's the point. The next impossible challenge is already underway. New loads, new threats, new extremes. And somewhere in America, in a room you'll never enter, the Blackout factory is getting ready. Because the lights, they can't go out. Subscribe if you want to see what we explore next.